So thank you for talk. Today I'll be talking about some work I've been doing for the last few years on formalizing in algorithms that come from the area of combinatorial optimization. So before I start, I will just try to introduce the area. So what is combinatorial optimization? So from the Wikipedia article on the subject, it's a subfield of mathematical optimization. So it's a subfield of applied mathematics, where one tries to find an optimal object from a finite set of objects. So this applies to many problems, especially important in computer science, but also in operations research and many other areas of applied mathematics. So example problems of that are finding a shortest path in a graph, a record graph, or finding a minimum weight or maximum weight spanning tree, computing a matching in a graph, flows, many other problems that you're all aware of. So this is the general area of this is the meaning of combinatorial optimization. So you try to find something as a solution from a finite set of possible candidates. So what is the goal of this project? So it is to have a formal library of graduate level results from the area of combinatorial optimization. So one specific textbook that we have focused on, and we almost finished everything in it, is this book on optimization by Bernhard Kota and Jens Fügen. And so it's like a final year math computer science book and first year PhD book, so it's relatively advanced. And also we have some research level results, so some formalizations of some papers that are interesting to the area, but that are not in books, for example. And our focus is on polynomial, on algorithms that have polynomial running time, worst case polynomial running time, because that's usually these algorithms have more interesting mathematical structure behind them. Usually problems with such algorithms have more interesting mathematical structures behind them, which allow for these efficient algorithms instead of just brute force algorithms. So in addition to having a formalization of the theory, another goal is to have a verified executable, a library of verified executable and hopefully efficient implementations of combinatorial optimization algorithms. So these implementations are usually in computer algebra systems. So many of those systems have algorithms for matching, flows, and matroids, matroid optimization, and so forth. So that's the second goal. Before I talk about this library, actually, 1 second. So here, this QR code is a QR code that takes you to the GitHub repository if you're at all interested in the code and in the formalization or knowing more about the papers, because it has more of it's a GitHub repository with a lot of information in it for those interested. So before I continue, I want to say that this isn't actually the first effort to formalize combinatorial optimization. It's one of the earliest areas of theoretical computer science that people ever tried to formalize. So you have algorithms for shortest paths like the Dijkstra's algorithm and Claude-Warshall that were done before, of course. There's flows algorithms that were done in Mizar, and approximation algorithms for optimization problems, and algorithms for linear programming. So many results exist in the area. But there is one specific weakness, which is that all these results, even if they're in the same proof of system, use different representations of the objects that you're trying to formalize, which means that they cannot interoperate or work together. So why did we set out to have that? So there are three main reasons. The first one is the mathematics behind these results is considered to be hard and interesting and needs verification, and it's some of the deepest mathematics in theoretical computer science. So formalizing that mathematics might lead to new insights and improved proofs, shorter proofs, and so forth. A second reason is what I said, is that we need to have, it's important to have, or we think it's important to have a library of verified software that does combinatorial optimization, and that has at least 2 uses that I can think of. There are some safety critical applications where a suboptimal solution to a combinatorial optimization problem might lead to loss of life or substantial loss of some substantial economic losses. And also a lot of these combinatorial optimization algorithms are used for mathematical proof discovery traditionally in computer algebra systems. Like people use them to find counterexamples or to establish bounds and so forth. So if you have a verified way of doing that, that will give those mathematicians more assurance in what they're doing and avoid some bugs. And lastly, as I said, one purpose of building this library is having just one representation where all the results are on which all the results are proved, or as little representation as possible. And also one methodology in which using which we prove, for example, the correctness of algorithms, so that whenever you're trying to prove something new in combinatorial optimization, you know that you already reuse what has been done because everything is on one representation, and you also have a methodology of how to represent an algorithm and to reason about it, for instance. So you don't need to come up with all of these things. You just focus on the mathematics of whatever that you think you're trying to formalize. So the algorithm started in 2000. This work I started in 2019 with in a collaboration with Kurt Milhorn from Saarbrücken, and it now grew up to almost 123,000 lines of formalization. And there are many contributors. I'm listing them here, but they're also on the GitHub repository. And initially, actually, all this work was just on my disk or separate repositories that came from either my own work or my own experiments and experiments of students, master students, and so forth. And 2 years or maybe 18 months ago, I started thinking, okay, we should actually make this into a proper library, and that's how we have GitHub repository. And now some students and some people still contribute. They do it just as pull requests, where you either fix something or modify something, or if you want to add something new, then what you do is you just add a new Isabelle session, which is the unit of Isabelle projects or buildable Isabelle projects. So all of that is a boring introduction, but that's the last one in the introduction. So the library covers what I think are all the fundamental problems in combinatorial optimization and has algorithms for all of them, in many cases, the fastest algorithms. So you have paths, shortest paths. For example, you have matchings, maximum cardinality, maximum weight matching, and many variants of that. You have flows, maximum flows, and minimum cost flows, and connections between matchings and linear programming. And you have also algorithms for optimizing matroids and redoids, which are a generalization of, some people see it as generalization of matrices, but in the case of combinatorial optimization, it's better to see it as a generalization of graphs. And we have algorithms for spanning trees and this traveling salesperson algorithm problem. Okay, so what is the goal of this talk? I want to go a little deep into the mathematics with you, just to give you a feel of what kind of arguments you need to formalize when you're doing combinatorial optimization. So what are the reasoning patterns, and what are the possible outcomes of such a formalization project from a mathematical perspective, and also from a library design perspective, if you want to start an combinatorial optimization library in your own proof assistant. I want to just tell you about the type of reasoning patterns and reasoning principles that you might want to do or to formalize, and the types of objects that you might want to represent there. And also briefly discuss future directions of the library. So I will give you a few examples of results in the hope that these examples illustrate the reasoning principles and data types that you need to define and so forth, and other library design aspects. So the first thing I will talk about is maximum cardinality matching. This is a problem in computer science, but also it's been studied in graph theory and many other areas. But the problem, as stated here, is more of the computer science version. So you're given an undirected graph, and you want to compute for that graph the maximum cardinality matching. So firstly, I want to define what is a matching. So if you're given an undirected graph like the one that we have here, a matching in that graph is a subset of the edges, such that this subset of edges is vertex disjoint, meaning no two edges share a vertex. So for example, for this graph that we have, the blue edges form a matching because they don't share any vertices among them. And it's also a maximum cardinality matching, because if you think about it for a little bit, there just isn't any other subset of these edges that would also be a matching, and that it has a cardinality bigger than 5 in this case. Okay, so that's the problem. What we did in the library, or the first project that I did in this library, was formalizing Edmonds blossom shrinking algorithm, which is an algorithm to solve this maximum cardinality matching problem for general undirected graphs. So not bipartite graphs, but general graphs. Okay. And the goal at the time was to formalize a correctness proof from a specific book that is associated with the C++ library. It's called Leda by Kurt Miller and Stefan Neyer from the 1990s. And this work was done mainly in collaboration with Kurt Miller, but TBS NIPCO at least contributed some ideas, but it's mainly with Kurt Miller. So TBS is the one who told me to not list him as a contributor, because that's what he said. So why is this algorithm interesting? So this algorithm, it was developed in the 1960s, and it is actually the first time that the publication of this algorithm and that paper is the first time that people understood the polynomial running time, worst case polynomial running time, to be the notion or a notion of computational or efficient computation or efficient algorithm. So before that, it wasn't clear what an efficient algorithm is. It wasn't formally defined. So brute force algorithms that just try all possible solutions were common, and there wasn't a clear differentiation. But this algorithm was the first one that demonstrates that notion of efficient computation. And from formalization and verification perspective, it is a complicated algorithm. So in any book, it's usually one of the more harder ones to prove correct. So let me try and take you a little bit through the algorithm without going so much into detail, just to give you a sense of what kind of mathematics is done there. So the algorithm goes as follows. So you have a top loop that does the following. You have a graph, it gets a graph and a matching in that graph, and that top loop in every iteration tries to make that matching bigger. Okay, how does it do that? It does that by computing an augmenting path, or so-called augmenting path. And if it tries to compute an augmenting path, if it finds a so-called augmenting path, it uses that augmenting path gamma to expand the current matching. And that's done by taking the symmetric difference of the matching, of the current matching and the edges in this augmenting path. So what is an augmenting path? It's a very important concept in most of combinatorial optimization, especially matchings and flows, but in many other special problems as well. So in the case of matching, an augmenting path is a path in the graph such that the first and the last vertices in the path are not covered in the matching, and such that it's a so-called alternating path, meaning that every two consecutive edges in the path are satisfy the following. One of them is in the existing matching, in the current matching, and one of them is not in the current matching that you're trying to augment. So as a simple example, here we have a small graph, and the two blue edges are matching because they don't share any vertices. This path is an augmenting path in that graph for that matching. Why is that? Because the first vertex and the last vertex are both not in the matching, as you can see, 1 and U6. And every two consecutive edges satisfy the condition that I told you, which is that one of them is in the matching and the other one is not in the matching. So this one is not in the matching, this one is in the matching, this one is not in the matching, and so forth. If you take the symmetric difference between this set, so matching, and this set of edges in the augmenting path, you will have matching that is one edge bigger, so 3 matching of cardinality 3. So this is the main idea of almost all matching algorithms, but also almost all offline matching algorithms, I would say. So matching algorithms that deal with a graph that you give it, not a graph that comes through like time. If you have the entire graph available, this is usually the schema of any matching algorithm, but also flows and flow algorithms operate in the same way. So the correctness theorem of all of these algorithms, including Edmonds-Blossom algorithm, depends on a lemma by Claude Berge. So it's called Berge's lemma from the 1950s. And basically, the lemma says a matching has maximum cardinality if and only if it has no augmenting paths. So if you have a matching and you cannot compute an augmenting path for that matching, then that matching is a maximum cardinality matching. And the proof of the lemma of this lemma is from the 1950s, and it has 2 directions, as you might expect for an if and only if statement. So the first direction is effectively boils down to showing that if you have a matching and an augmenting path, and you take the symmetric difference, this will give you a bigger matching. And that was very straightforward to formalize, so nothing interesting to say here. And the other direction is the harder one, which is to show that if you have a maximum cardinality matching, then you which is to show that if you don't have an augmenting path, then this matching is a maximum cardinality matching. So the proof goes by contradiction. So you assume my current matching M is not a maximum cardinality matching, and you assume that there is another. So from that assumption, you can derive you can show that you can easily show that there's another matching M prime that is bigger than the matching M, right? And from there you try to derive an augmenting path, which proves the theorem of contradiction. So this is but the core of the proof, or the hardest part of the proof, is the following. And it's a technical thing, but I want to go in it just to give you a sense of the kind of mathematical proofs you want to do when you're proving things in combinatorial optimization. So we say, okay, we have this matching M and this matching M prime. If we take their symmetric difference, you need to show that this symmetric difference, set of edges in the symmetric difference, will be either will form a graph, and that graph has connected components that are one of 3 categories. It's either a singleton vertex, an alternating path, or an even alternating cycle. So an alternating cycle that has an even number of edges. And this is actually, this is quite an annoying proof to do in a theorem prover. So we kept trying to do it, but when we failed, we actually came up with a proof that avoids this step, which is a step that is in all standard textbooks and so forth. That top of Berge's lemma, which is so that's the first outcome that you could expect from formalizing these kinds of results. Another thing in this algorithm that I want to point out, and which is very common to combinatorial optimization algorithms, is that you usually have a big while loop or a big computational object that you want to reason about. In our case here is you have to search for augmenting paths somehow, so you need an algorithm to do that. And I won't go into the details, but I just want to show that the pseudocode is quite complex, and when you try to formally prove the correctness of something like that, you need a lot of you basically need to be careful and principled in how you do it. And this is very common to combinatorial optimization algorithms that solve problems like flows and matchings and so forth. So when you prove when you try to reason about something like this, it's similar to program verification. It just is a bit higher level than program verification in the sense that instead of reasoning about pointers and so forth, you're reasoning about, you're trying to connect this while loop to deeper mathematical results that you have, like Berge's lemma or other results. So you have here some initialization, and you have a while loop with a complex mathematical termination condition, and you have 2 execution branches. So it is quite annoying to handle formally. But what does it mean to prove something like this correct? It has 2 meanings. The first one is that if it returns a result, then that result will be correct. So this is, you can call this partial correctness. So in our case, if this loop returns a result, that result will be an augmenting path. And the second direction is total correctness, which is, and the harder part of total correctness is not just showing termination, but showing that if you terminate without finding a result, so in this case, without finding an augmenting path, then there is none that exists. And in our case here, we construct a certificate that shows that no such augmenting path exists from the values of the program variables. Like we always show that if it terminates without finding something, the values that are in the variables can be used to construct a certificate to show that no augmenting path exists. Yeah.
Yeah. So I want to ask: do you transfer these algorithms that are imperative faithfully to Isabelle, or do you convert them to functional style and then?
No, functional programs. Yeah, I was going to talk about that. Yeah. That's an important question when you're formatting these results. Another thing you want to reason about, or how do you prove partial or total correctness? You do that by stating and verifying so-called loop invariants, which are basically statements about the variables in the algorithm that are preserved across the loop's execution. So in the case of Edmonds Blossom algorithm, we have 18 mathematical loop invariants. So it is, and these are loop invariants that have like something. I don't know. It's well, you can say it's a meaningless statement. I will just say it anyway. I hope, in the hope that it conveys some intuition. So these are all invariants that have, not all, but most of these invariants have some mathematical content rather than just low-level invariants about pointers and things like that. These are some you talk about some properties of graphs, or some properties of augmenting paths and so forth. So in fact, when doing this, formalizing this proof, we found that there are 18 invariants that are needed, otherwise you cannot get the proof. And the proof in the later book that we started from has only identified 11 of those invariants, so that was interesting. I would say that this isn't the only proof though. So there are other books that I didn't ever formalize the proofs. I don't know if, my guess is that they're complete, but I don't know. But the one that we tried was incomplete. And indeed the author, Kurt Milhern, of that book, after, this book is like 20-something years old at the time. So he said that there was a specific step in the proof that he never understood until we did the formalization. So this is an interesting outcome of formalizing the combinatorial optimization. I think it's one area of computer science where a lot of proofs are not understood or incomplete, in fact. So by talking about Edmonds Blossom algorithm, I wanted to convey to you also what are the design elements of a combinatorial optimization formal library. So one thing you need is a graph representation, and that graph representation has to accommodate two things. It has to work for executable algorithms, because as I said, it's very practically useful to have verified combinatorial optimization software. So you want a graph representation that is executable, but at the same time also suitable for mathematical and abstract reasoning, because you really are proving serious graph theory as well. You also want lemmas and reasoning principles that handle a lot of reasoning of combinatorial reasoning about cases, like for example, connecting components of a graph, or matchings or alternating paths. And of course, you need a way to model the algorithm, as you were asking like a second ago. How do you actually model the algorithm? So in our case, we just modeled it as a recursive functional program. And the program state, we just modeled it using records, and loop invariants are just simply Isabelle predicates on those records or states. But there are better ways to model programs with different pros and cons. But in the case of combinatorial optimization, using recursive functions was enough, because what we were interested in is making sure that the mathematics is correct and just having any executable program rather than a very efficient one. Another problem that I want to discuss with you, but it will be much more brief, is online bipartite matching, that we also did some work on it. And this is a different setup. So you have a bipartite graph, so that's more special than a previous problem. But on the other hand, you have your input arrives online, which means that you don't know the whole input as you're doing the computation. So with every piece of the input that arrives, you have to make a decision. Do you take this piece into your final solution, or do you disregard it? And you cannot retroactively change your decision. So for instance, here you have a graph. So this is an offline side, which you know, this is your side. And the online side, which is the other side, arrives vertex by vertex, and each vertex comes with associated incident edges on it. And for example, when U1 arrives with its 2 edges, you have to make a decision right now whether you take either one of those edges into the matching or ignore them. And once U2 arrives, you cannot change your decision, and so forth. So the whole graph arrives in this online way. And we've verified the correctness of an algorithm called ranking by Karp and Vazirani. And this algorithm is actually quite important because its generalizations are used in most mathematical and analytic analyses of online markets, like most famously the AdWords market by Google. So the only mathematical model of that is an extension of this algorithm. So it's quite important for within computer science. So what is the algorithm? The algorithm is very simple. Your offline side, you randomly permute it once, and then when an online, when you have a vertex arriving in the online side, you just take the edge, like the edge that is connected to the topmost offline vertex that is free. So here, for example, V1 arrives, you take that edge because U3 is the topmost ranked vertex, and that's free. V2 arrives, you take the edge connecting it to U1, so you match it with U1. V3 arrives, you try to match it to U1, but you find that it's not free because it was matched to V2. So you go to the next thing, which is U2, and so forth. So the algorithm is very, very simple, but its analysis is not. So the algorithm, the circle of the algorithm is the complete opposite of Edmund's Blossom algorithm, where it's very, very simple and you can state it in 1 minute and to be fully understandable. So you take a random permutation of the offline side, and then the online side, and for every vertex arriving, you just choose an edge in the same way I just mentioned. And what is the correctness of this algorithm? Here is the complexity of this. So when I say this algorithm is correct, I mean that on average, and here I'm going to say it in the way it's stated in the on the papers, in the papers where this, like in the third computer science papers where this study, so it's not very rigorous. So they write it like this, and that means that on average ranking, so this algorithm will compute a matching whose cardinality is lower bounded by the maximum cardinality multiplied by that factor, 1 minus 1 over the natural exponent. And that actually is a bound that occurs in almost all online matching algorithms. Okay, so to formalize that, you firstly need to formalize what that means. So you want to say that this is the expectation of the output of ranking, modulo also permutations that you can do to the offline side. And then also this statement only holds in the limit when m as m grows. So you need asymptotic reasoning and probabilistic reasoning to even state the correct what it means to be correct. So, like this algorithm shows that if you want to do serious combinatorial optimization, you will also need to talk about online algorithms, which is a different mode of computation. The way we're doing it is just by recursion of our list of inputs, but that's a naive way. If you want to prove more interesting properties, you might want to have a better model of computation. Also, you will need asymptotic and reasoning about randomized algorithms. So we're using here 2 things that were done by Manuel and co-authors. So thanks, Manuel, for that. So the proof of the algorithm, I want to go slightly to the mathematics again and not to the formalization. So the proof of the algorithm was studied by 5 previous authors. Actually, there's a 6th one that I didn't put here, but it was studied many times, and it's understood to be a proof that is not rigorous and not understandable. And all these papers are just trying to improve the truth. And we chose, with Christopher Madlener, one of my students, we chose to formalize one of the papers, which is called Online Bipartite Matching Made Simple. And the main claim of the paper is that it provides a simple combinatorial proof. And you can find the paper in this QR code if you're interested. It was presented in ITP 23. And I won't go through the formalization, of course, but I will just tell you that the paper had a big hole, which was that a certain lemma holds because of an easy structural observation, and the way that easy structural observation can be proved is just by a figure with just some graph and some like a specific case, a specific graph and specific matching, and that was the proof. But when you formalize this actually filling this hole was 60% of the effort. So that's I find that to be an interesting outcome. That if you try to formalize, and I don't think even it has to do with formalization. If you just try to verbally describe that graphical argument, it will be very hard on pen and paper. But they didn't do it. They just drew a figure and then said it's an easy structural observation. So I will now talk about this last thing, which is the connection of matchings and linear programs. So I won't be spending so much time here. So I just want to say that matchings and linear programs have been connected since the 1960s, and many, many important insights into the computer science came out of that connection. Maybe one last main result is the parallel, like the proof that computing perfect matching, which is a certain type of matchings, can be done efficiently on parallel machines, and that came due to insights from the connection between matchings and LPs, and it's many other important results came out of that connection. So we proved a few theorems on that. We didn't really, they're standard theorems in textbooks, but they're not like state-of-the-art research or anything. So one of them is this so-called matching polytope theorem, which is that the polytope formed by the linear, or by the faces of the linear program representing matchings has only integral corners. And the proof wasn't very surprising, but it just made us know that you need even more concepts and things in a combinatorial optimization library, like for example, talking about matrices and linear programs and the duality theorem and polyhedra, and also it had a lot of complex and annoying geometric reasoning. Other works that I will not be able to say anything other than the title is work on minimum cost flows. So this is a recent paper that we presented in March 2024, where my student Thomas Ammer and myself verified the fastest algorithm for minimum cost flows, which is Orlin's algorithm. And this algorithm uses a technique called scaling, which is used in other algorithms, like used to design the fastest algorithms for other problems, not just minimum cost flows. So for matching, there are very fast algorithms with scaling. So that's another thing that we did in this library. And also we have an algorithm, we have a formalization of algorithms for optimizing matroids and redoids, which are abstractions of graphs, as I said. At least that's how I see them, but others see them as abstractions of matrices. But in our case, it's useful to see them as abstraction of graphs because these algorithms can be used to compute spanning trees and so forth. And this is it will be presented in 1925. And lastly, we have, this is not published, but we have an approximation algorithm for traveling salesman called Christopher's algorithm, which was done in 1971 and was only improved recently in 3 years ago by a factor by 1 over, I think, like 1 part in millions. So that the approximation ratio. So it had the record of the best approximation algorithm for traveling salesperson for 50 years. It uses the advantage from a formalization perspective is that it uses like algorithms for spanning trees and maximum weight matching. So it combines a lot of things in the library to come up with something else. So one thing I didn't talk about, so all what I was talking about really was about what kind of mathematical reasoning do you need to do on what kind of lemmas and what and things that are more abstract. But if you remember, I said one goal is to have verified executable algorithms, meaning code that runs. And for that, you need data types that allow that code to run. I will focus only on the data types. There are other aspects of having code that runs, but I think the most interesting one is data types. So I'll focus particularly on different representations of graphs that are suitable for executability and also for mathematics and how that's managed, in our case at least. So you need a representation, as I said, that works well for mathematical reasoning, abstract mathematical reasoning, and like, for example, proving Burr's lemma. And what we found, and I think what most people believe, is that the best kind of representation to do this kind of mathematical reasoning is just using the default set representation in your own proof assistant. So for example, here, just a directed graph is just a set of pairs of vertices. And that allows you to use a lot of the old automation that is already developed for sets, for instance. But not only that, it also allows you to gloss over irrelevant details when you're talking about the mathematical argument for why the algorithm is correct. So, for example, here the neighborhood of a vertex can be just a set comprehension like that. The problem with this kind of representation, though, is that it is not immediately executable. So, so how can you overcome that? So one way we do it, the way we do it, is we use the so-called abstract data types, which is something that's well known in many programming paradigms, like functional programming. So that's what we do. So we have, for every concept, we have a mathematical representation, like for example, sets in the graphs, and abstract data types, which represent the executable representation. So for a graph, so what is an abstract data type? You just have an interface for whatever the concept you're trying to define. So here, for example, we talk about directed graphs. What is a directed graph? What are the, so this is just a snippet from a book draft that's currently in press by Tobias as an editor, but I have a chapter on it on graph algorithms. I'm using this, like instead of showing you actual Isabelle syntax, this I hope is more readable. So you have an abstract data type of graphs. And what is that? It uses two abstract data types, one for maps, which is an adjacency map. So it's something that maps a map that maps every vertex to its neighborhood. And it also uses sets with choice. And the interface of this abstract data type is some functions for updating the graph and looking up whether a vertex is connected and so forth. And there are many of those functions. And as you can see, there's a lot of details when you're talking about data types that you want to be executed in comparison to the mathematical ones. So now, for example, for this other data type, for this abstract data type, like the neighborhood is a functional program basically. So it's this, instead of the initial neighborhood that was just written as a set comprehension, mathematical set comprehension. So now this leaves us with a problem, which is how do you do you have a lot of facts proven about the mathematical data types, or the sets of pairs, for instance. Now you want to use these facts about the executable algorithm that is specified in terms of abstract data types. So do you have to reprove these? No, you don't. And there's this notion of data type refinement, where you basically, it's a three-step recipe. So for every data type, you come up with an abstraction function that connects the executable version of that data type with the mathematical version. So for example, here we have this thing that abstracts a directed graph. So it takes an adjacency map and gives you a set of pairs, and it's defined that way. And based on these abstraction functions, you prove equivalences, so lemmas that build on top of each other, that show equivalences between the executable representation and the inexecutable ones. For example, here we say a vertex is in the neighborhood of that is computed by the executable neighborhood function, if and only if this edge is in the abstract version of that graph. And then based on that, you prove this. And we have automation, which is rather ad hoc, but it works, that allows you to reuse mathematical facts in the context of the executable data types. So I don't think I have much more time. I mean, you started 3 minutes late, but
yes, and if you want to have a few questions.
Yeah. I'll just say three things. So we have three goals from a library design perspective. The first is to have a single graph representation. We still have more than one for the undirected, multi-graphs, and hypergraphs. So we want one representation. And we want to study more the way to model algorithms, so instead of just functional programs. So there are other ways to do it, which have pros and cons. And lastly, we want to use better ways of doing this data type refinement instead of the ad hoc way that I just described. So thank you very much. And yeah, I look forward for your questions. Yes.
Is there a reason why you're having it as a separate repository and not in the archive?
That's a very good question. The only reason is that we're still modifying. I mean, there is, so the basic representations are in the AFP, but the ones in the AFP are already stale because we're still continuously modifying them. And it's a good question. I mean, the only, it had, like, I just didn't have the time really to do that. But the advantage of putting it on GitHub is also it allows you to easily use pull requests and all that, but to change things. And on the AFP, you would have to just push things and then see, so if you're working with contributors that you don't know very well and want to change something in their presentation, they will just push things. And it's not optimized for continuously changing things, I think.
One question. So did you already formalize, results on the complexity of these algorithms, or do you plan to do so?
Yes, I mean my last point about the model of the way we represent algorithms, we want to represent them in not just simple function programs, but in a deeply embedded computation model that has resource semantics, like running time semantics. So we plan to do that.
Okay.
But that's
Some more questions? Okay. Yes.
So you have many variants of rights, directed, undirected, labeled, and labeled, and so on. Do you have a kind of hierarchy?
Well, that's what I was saying. Like we want just one base representation that all these things are kind of special cases from. That could be a hierarchy. Currently, we have undirected, one representative of undirected, one representative of directed, one representation of hypergraphs, and one representation of multi-graphs and so forth. But yeah, we want to just boil the essence of that, to have one representation and then have a hierarchy, as you're saying. So that's something to do, I guess. Yeah.
Okay, so I have a related question. So do you use the transfer packages for Isabelle to transfer results from the abstract to the concrete?
So because I didn't have, so actually all your questions, so this also is covered in the last slide. So the refinement, there are two better, so the current ways we're doing refinement is just by using Isabelle's basic automation. So it's classical reasoning, introduction and instruction rules, but the best way to do it is conditional transfer, like the way they do it in the recent paper by Cyril and co-authors. That's the best way, I think, to do it. And we don't have that in Isabelle. We have transfer, but not conditional transfer.
Well, so thank you very much.